Today we're going to do a classic example which comes from the maybe first third of an abstract algebra class. This would be like an undergraduate abstract algebra class. And in particular, we're going to classify all groups of order 8. And so since this is coming from the beginning part of the class, we're not going to use like the fundamental theorem of abelian groups or anything. And I've got a little spoiler over here that there will be 5 in the end, but we'll get to that point. Okay, so let's maybe see how we can do this. So we're going to first suppose that G is a group of order 8. And then we'll show that G is in one of 5 isomorphism classes. Okay, so by Lagrange's theorem, so remember Lagrange's theorem says or implies that the order of a subgroup divides the order of a group, but that means the order of a cyclic subgroup divides the order of a group, which means the order of an element must divide the order of a group. Well, there are only a couple of divisors of 8. There's the number 1, 2, 4, and 8 itself. So that really simplifies the case. So Lagrange's theorem implies the possible order of elements is 1, 2, 4, 8. Now we can't have all elements of order 1 because that means everything would be an identity, but we know that the identity is unique, which means non-identity elements will have order 2, 4, or 8. And now we're going to work through some cases. So let's start with our first case, which is the simplest, and that is G has an element of order 8. And let's say that element, we'll call it X. So we've got X as an element of G, which is order 8. But if we take the cyclic subgroup generated by X, we'll get EX, X squared, X cubed, X to the 4th, X to the 6th, X to the 5th, I should say, X to the 6th, and X to the 7th. Those will be those 8 elements. But we've got a subgroup that has the same order as the group, which means this subgroup is the entire group. But that means G is a cyclic group of order 8. But if G is a cyclic group of order 8, we know that it must be isomorphic to Z8, just kind of by the uniqueness of cyclic groups. Okay, so that gets our first isomorphism class over here, which is Z8. Okay, now let's move on to our next case. Now we're moving on to our next case. And so the second case will be that G does not have an element of order 8 or 4. So I'll say element of order 4 or 8. So this is maybe the next simplest case after this case right here, Z8. So that means every non-identity element has order 2. So let's write that down. Every non-identity X in G has order 2. That means X squared is equal to the identity. Now here we're going to prove a little bit of a subclaim. And this subclaim is a pretty standard homework exercise from the maybe first day that you learn about groups in a class like this. And that would be G is abelian. So that's our subclaim, like I said. So G is abelian. So let's look at the proof of this subclaim. So let's suppose that X and Y are in G, but that means that X squared is the same thing as Y squared, which is the same thing as the identity. And furthermore, we know that XY quantity squared is the same thing as YX quantity squared is the identity. And that's because everything has order 1 or 2, but that means if we square anything, we get something that's the identity. Okay, so now we're going to start with XY, and we'll multiply by a certain version of the identity. So we'll take XY and we'll multiply by YX squared, and then we'll expand this out. So this will be XY, YX, YX by squaring out this X or this yx right here. Okay, great. But notice that this y will cancel with this y because y squared is the identity. And then we'll have x times x, but the x will cancel with the x because x squared is the identity, leaving us with yx. So we started with xy and we got yx, but that means we've proven this claim that G is abelian. So let's move on from there. So we've just proven that if we've got a group where every non-identity element has order 2, then that group is abelian. We also have kind of a parent group of order 8 here. Now, if you think about groups of order 8 that you might know already, where everything has order 2, there's kind of an easy first guess at what this might be isomorphic to, and that would be 3 copies of Z2. And that's exactly what we'll get here. But we need to figure out how to define such an isomorphism. And here's how to do it. So let's take non-identity elements, x, y, and z from G, satisfying one other rule that x times y is not equal to z. So that's possible. If that were not possible, then we wouldn't have 8 total elements. This kind of choice is possible because we've got 8 elements. We've got enough elements to make this choice. Great. Next, we'll define the following map. So I'll call it phi, and it goes from 3 copies of Z2, so I'll say Z2 cubed, and then ends at G, and it takes I, J, K to x to the I, y to the j, and z to the k. Great. Now we first want to show that this is a homomorphism, and then we'll show that it's injective. Those are the only 2 things we need to show. You might think we need to show that it's surjective, but because these have the same size, injectivity will imply surjectivity. This guy clearly has 8 elements, and this group also has 8 elements by design. Okay, so let's prove first that this is a homomorphism, and we'll do that by looking at phi of I1 plus I2, J1 plus J2, and K1 plus K2, and see if we can factor this out. So this is going to be x to the power I1 plus I2, y to the power J1 plus J2, and z to the power K1 plus K2 by the definition of our homomorphism. And then given our group operation on the right-hand side, which is written as multiplication, we know that this is equal to x to the I1, x to the I2, and then y to the J1, y to the J2, and then z to the K1, z to the K2. Great. And then next, we know that this thing is abelian from our previous claim, so we can move things around as necessary. So this will be x to the I1, y to the J1, z to the K1. Again, like moving things around like I said, and then x to the I2, y to the J2, and then z to the K2. But that's exactly phi of I1, J1, K1 times phi of I2, J2, K2 as necessary to prove that this is a homomorphism. Okay, good. Now let's prove that this is injective. So now we'll prove that this map is injective now that we know it's a homomorphism. Just to reiterate, we don't need to prove that this is injective and surjective. And that's because we know that these 2 groups have the same size, so one will imply the other. So we'll use the standard method of proving something's injective, which is analyzing its kernel. So the kernel is trivial if and only if this is injective. So let's suppose we have something in the kernel. So let's suppose that phi of I, J, K is equal to the identity. And let's break this into cases. So the first case, which I'll slip over here, is I equals J equals K, which equals 0. But in that case, we're all done, because that means we've started with the identity. We want to show that the other cases are impossible. So let's do those one at a time. So our first case would be one of these is non-zero. So let's write that. So 1 is not equal to 0. And then I'll just work this as example. For example, I is not equal to 0, but J and K are equal to 0. But what does that tell us? We have phi of 1, 0, 0 equals the identity, but that means that x equals the identity, but that's a contradiction because we assumed that x, y, and z were non-identity elements. Great. And then number 3 is 2 are non-zero. And so let's take I and j to be non-zero in this case. So that means we get phi of 1, 1, 0 equals the identity, but that means that x times y is equal to the identity. But since an element is its own inverse, this means that x is equal to y, because x is the inverse of itself, and by this line right here, y is the inverse of itself. But I think I said this in words, but forgot to write it down. These non-identity elements are distinct. And so that contradicts the distinctness of these non-identity elements. Okay, so now let's look at the fourth case, which is all 3 are non-zero, which means we get phi of 1, 1, 1 equals 0, or equals the identity, which means x, y, z equals the identity. And then we can multiply by z. Since z has order 2, that'll cancel it from the right. And we're left with x times y equals z. But that's a contradiction from this assumption right here. So 4, 3, and 2 are impossible, which means that 1 is the only possibility. But 1 being the only possibility means the only thing in the kernel of this homomorphism is the identity, which means this thing is injective. Okay, so this is an injective surjective homomorphism, which means this is an isomorphism, which fills in another line over here of our possible isomorphism classes. And I'll write this one right here. We have Z2 cross Z2 cross Z2. I'll write it out. Okay, now let's move on to the next case. Okay, so now moving on, we've got our third case, which is that G has an element of order 4, but not order 8. Because we looked at the case when it had an element of order 8 already. And so let's call this element X like we've been calling our building elements already. Okay, so what does that mean? That means we've got a cyclic subgroup generated by X, which is a subgroup of G. And then furthermore, we know the order of X in G is equal to 2, which tells us that X is in fact a normal subgroup of G. So that's, again, one of these kind of standard exercises to show that if you have a subgroup of order 2, it must be normal. Then furthermore, if it's normal, we can look at the quotient group. So G mod, this cyclic group, is a quotient group of order, this index, but that's a quotient group of order 2. There's only a single group of order 2, and that's Z2. But that means that this is built out of 2 pieces. So the coset represented by the subgroup itself, and then one other coset. And I'll represent it as a right coset, although it's kind of more standard to represent it as a left coset. But I think like in this setting, it makes it work a little bit better. So I'll say this is X, Y. And then our multiplication table is just kind of as is standard here. So we know Y squared is the identity in this quotient group, which means Y squared is inside this cyclic group generated by X. Okay, so we also can say that G has the following elements. It has the identity X, X squared, X cubed. So that's the cyclic subgroup. And then it has this bit over here as well, this right coset generated by Y. So that'll be Y, and then XY, and then X squared Y, and then X cubed Y. And those are 8 distinct elements, again, by some stuff that we know about cosets partitioning a set. Okay, so let's note that YX is not on this list, but we know that YX is definitely within the group. that means that yx must be one of these. And that's going to break us into our other cases. So the first case will be yx is xy. That means we have an abelian group. The second case will be yx equals x squared y. And then the third case will be yx equals x cubed y. So let's look at those one at a time. So first, yx equals xy. So in other words, we have an abelian group. And this kind of motivates another kind of guess for the isomorphism class here. And here we'll define the following map. So we'll go from Z4 cross Z2 into G. And what we'll do is we'll map IJ to, let's see, X to the I, Y to the J. And I guess built into this is the assumption that Y squared is the identity. But I think in this case, Y squared has to be the identity. Maybe fill in those little details on your own. That would be a nice exercise. Okay, but let's notice that we've got a fairly similar map to what we had in this case over here. So I'll leave it as a homework exercise to work out the details that this is an injective homomorphism, and thus, because of size considerations, it's in fact an isomorphism. So that gives us our other abelian isomorphism class of Z4 cross Z2, leaving us with these two cases down here, which turn out to be non-abelian. And those are going to be built off of these leftover cases here. So let's maybe do that. Okay, so let's recall where we are. We have G, which is a group of order 8. It has an element of order 4, but not an element of order 8. We looked at the case when that setup was abelian. Now we're going to look at the case when that setup is non-abelian. And that leaves us two kind of subcases. The first is that yx equals x cubed y, and the second is that yx equals x squared y. We're going to, in fact, show that this is impossible. So let's notice if yx equals x squared y, then that means that x is equal to y inverse x squared times y, which means that x squared is equal to, let's see, y inverse x squared y inverse x squared y. But notice things cancel from the inside to the out. So y times y inverse, that's the identity. And then x squared times x squared is x to the fourth, which is the identity because it has order 4. And then y inverse times y is the identity. So we end up with x squared as the identity, which contradicts the fact that x has order 4, because this would say that x has order 2. Okay, so like I said, that just brings us to an immediate contradiction, meaning that this setup is impossible. So that leaves us with just this case when yx equals x cubed y. So let's look at that. And now this is actually going to build into two sub cases. So I'll maybe make those as these kind of orange dots. So we know that y has to have order 2 or 4. It can't have order 8 because then we'd have a cyclic group. Can't have order 1 because then it would be the identity element and it would commute with x. So all that's left is for it to have order 2 or 4. So our first subcase will be y squared has order 2. But notice that means our group can be written as being generated by x and y, where x to the fourth and y squared are both the identity. And then also yx equals x cubed y. But those are exactly the defining properties of the dihedral group of 8 elements, D4. So in other words, the symmetries of the square or the regular fourgon. And there's not really much else to check there because those are the defining properties of this group. So let's put that down here as our fourth isomorphism class. And that leaves us with one more thing, and that would be the order of y equals 4. So I was careful to write this as order y equals 4 instead of the y to the fourth equals 4 because that would include this y squared term as well. Okay, so now let's work on this. So we know from a previous discussion that y squared must be in the cyclic subgroup generated by x. Well, why is that? Well, that's because if we look in the quotient group, x y times x, y as elements of the quotient group, those two cosets, give us x, y squared. But we also know that that's two non-identity elements of a group that's a cyclic group of order 2. So this has to be equal to the coset generated by x. But that means that y squared is in there. But then also, the order of y squared equals 2. So we're looking for something inside of the cyclic subgroup generated by x that has order 2, but there's only one thing within that cyclic subgroup that has order 2, and that's x squared. So that tells us x squared is equal to y squared. And that gives us a presentation for G. So G is now generated by x and y. And it has the following rules. So x to the fourth is the same thing as y to the fourth, which is the identity. X squared is the same thing as y squared. And then finally, yx is the same thing as x cubed y. But those are exactly the defining properties of our last group of order 8, which is the Quaternions. So sometimes this is Q8. And if you know the Quaternions in the IJK form, this would be like having x identified with I, y identified with j, and then xy identified with k. But this gives you the same sort of presentation. Okay, so we did it. We started with a group of order 8, and we showed that it had to fall in one of the following 5 isomorphism classes. And that's a good place to stop.